All right, so we were talking about coordination compounds, and as we talked about, they do contain two things. They're basically kind of like an ionic compound. You basically have either a counter ion and also a complex ion. And as we saw and as we talked about, they really can be either charged. So if you have a positive counter ion, you will have a negative complex ion. And if you have a negative counter ion, then your complex ion will be positive. And they're really there just to really sort of balance each other out. Like I said, like a normal ionic compound. Um, we talked about naming these guys, and the counter ion is pretty much named just like normal. So whatever the name is, regardless of really how many you have of them. If you have multiple counter ions, it doesn't really matter. You just kind of use the name. So if you had multiple potassium ions, it would just be potassium. If you had, say, a negative counter ion like nitrate, and you had multiple of those, it would also just be nitrate. The complex ion part, we do name the ligands first in alphabetical order, regardless of prefix. We do the metal at the end, and the metal will have a Roman numeral with it. The metal name, though, will depend on whether the complex ion is positive or negative. If it is positive, then it is just like the normal sort of periodic table element name for the metal. If it is a negative complex ion, then the metal goes with kind of that old school name, like we talked about, that ends in ATE, like ferrate, cuprate, plumate, zincate, all those kind of guys. We also talked about coordination number. Coordination number, again, is the number of atoms that are directly bound to the metal in the complex ion. Remember that it's not always, say, the subscript that you may see in the formula, because some ligands are monodentate, some are bidentate, and so forth. So again, if you had something like water, water being monodentate, binding through the oxygen. So for every water that you have, in terms of coordination number, you do get basically one. Now, if you had something like ethyl endyl diamine, which looks something like this, and in this case, basically at each of these nitrogens, that is where it's going to bind into the metal. So you basically kind of a 2-for-1 type situation that's occurring with that. And then we have something like EDTA, which can bind in like 6 places per molecule. So you do have to sort of keep that into account. I would say probably your endoethyl and probably your oxalate was the other one that we kind of looked at, are probably your majority of bidentates, or very common bidentate ones that you will see. Oxalate as well at each of those oxygens can bind in to the metal. Any questions on any of that there? All right, so the next thing we're going to talk about is a little bit about isomers of these sort of complex ions. And isomers are essentially the same formula, but usually they have some type of different connectivity. And because they have that different sort of connectivity of how they're put together, they are different sort of structures, if you will. They are different compounds, and they will have different sort of properties as well. There's a few different types of isomers we're going to talk briefly about. There are structural isomers, which have different bonds. And with that, there's two types of structural isomers. There's coordination isomers and linkage isomers. And then there's stereoisomers, which have the same bonds but different sort of three-dimensional orientations in space. And that gives us geometric isomers, which are cis or trans, and also optical isomers as well. So let's talk a little about coordination isomers, which fall under structural isomers. And in this case here, we have two coordination compounds. And the difference is really in what is sort of our counter ion and what is part of the complex ion. So here we have our counter ion here, which is our bromide. And here, part of our complex ion, where our chromium's in the middle, we have our 5 ammonias attached to it. It's 5. And here we also have our sulfate basically attached as well. So in this first one, sulfate is part of the complex ion. The bromide, again, is the counter ion. On this one, it has the exact same formula, basically. We got basically our 5 NH3s, our 1 Br, and our 1 sulfate. The difference, though, is here the sulfate is actually acting as the counter ion here. And part of our complex ion is actually that bromide gets incorporated in there. So with our 5 ammonias that are attached, the bromide here is actually a ligand that is attached. So these are coordination isomers. They have exactly the same sort of elements involved in their formula. But in this case, one case, the sulfate is actually part of the complex ion, and the other case, it's acting as a counter ion. And really the same thing with the Br in this particular case. Because in each of these cases, we have really a different ligand in the complex ion. It will give it probably some different properties from each other than having the identical type properties. Now, another type of isomer like this is known as a linkage isomer. And the linkage is pretty much what the name implies. It is how the actual ligand attaches or binds in to the metal in the complex ion. Now, if we took something like nitrite, which is NO2 minus, we actually have 2 options for how this guy could kind of work or attach. It can attach through the nitrogen to the metal, but it could also attach through the oxygen. Again, it's not going to do both at once here, but it has the option of both the nitrogen and the oxygen to attach. So in the top case here to our cobalt in the middle, the attachment point here on our NO2 minus is actually through the nitrogen. And we could easily as well have that attachment point here through one of the oxygens in the case here. And that is what's known as a linkage isomer. Here we're using the same ligand, but within that ligand, we're using different sort of attachment points to the metal because we actually have more than one option. We have both the nitrogen and the oxygen, which can act as a Lewis base in this case and donate some electrons over to our cobalt, which again is acting as a Lewis acid. Question on that? Now, stereoisomers are a little bit different as well. They are sometimes referred to as geometric isomers, and that gives us cis and trans isomers. Now, cis and trans isomers occur a lot in organic chemistry as well. And basically, cis means the same side, and trans means really opposite sides. And in organic chemistry, what we're talking about a lot of times is like a double bond. Either the groups are on the same side or opposite sides, basically, of a double bond. And same idea here in this type of arrangement with complex ions, we'll get certain groups kind of on the same side or above the plane of the molecule or opposite sides of the plane of the molecule in the center is what we'll get. So with these, we get the same atoms, we get the same bonds, but we do get different bond angles because of the location of these different ligands. These are common in square planar complexes. So for example, here, this is a square planar, basically makes a square within the plane. And if we look at the top one here, this is the cis. So you could think of these two guys as being on the same side of the plane there, and the chlorides also as being on the same side of each other, and that's going to be cis. Here on the bottom is trans, which means opposite. So you can see kind of like the ammonias are on opposite sides here of our square. And also our chlorides are on opposite sides of the square, and that gives it trans. This also, because of the arrangement and sort of where they're attached, will give the cis and the trans different properties as well. They won't be identical. As you can just even see with the color there, description, one is really yellow and then one's more like a pale yellow because of the arrangement of those ligands. We could also see it in more of an octahedral sort of arrangement here with a coordination number of 6. Previous one was coordination number 4. And on the first one here, we have trans. And what we could see is if you think about sort of this guy here as being the plane of the molecule, we have a chlorine above and below sort of the plane of the molecule, and that is on opposite sides. And that is trans. Cis is, again, if this is sort of the plane, we have these guys sort of on the same side above the plane, and that is what is referred to as being cis in this case. Again, each of these will have some different properties depending on it. As you can see, though, the exact same formula, which makes them isomers as well. Now, optical isomers are isomers that have an effect on plane polarized light. Optical isomers have non-superimposable mirror images and are chiral. So chiral basically means that if you have a chiral molecule and you put it up against a mirror and it reflects out into the mirror, and if you take the mirror image out and try to put it right on top of the original image, it will not fit perfectly. There'll always be something sort of out of place based on the location. Very common example of that is you put it up in the mirror, you get this hand staring back at you. And if you pull out this hand from the mirror, you can do whatever you like. You'll never be able to get it to sit correctly. You could get like the thumbs to be on the right side, but one's palm up, one's palm down, which is not the right orientation. You can flip them both palm down, then the thumbs are like on the wrong side. So that's the deal with sort of chiral molecules. When you take the mirror image out, you could rotate it around as much as you like, but because of the angles of where like the ligands, for example, are attached, there will always be something just slightly off and won't really line up with the original image. And that's different than something that's sometimes referred to as being achiral. An achiral molecule has a mirror image where you pull it out and basically you could just plop that guy right back down on top of the original guy and it'll fit perfectly. These type of isomers are sometimes referred to as enantiomers. And here's plane polarized light. We send it through a filter and you get sort of light going in both directions. And there's our hand example. And if we look at some of these sort of examples here, we have these two isomers are mirror images that cannot be superimposed. So let's take a look here. Bring it a little bit bigger. So this is the original image here, our original isomer. And then we have our mirror image reflecting back. So again, obviously it reflects sort of right into the mirror. The deal though is when it reflects back, it actually creates a different type of bond when we sort of reflect this back. So in the original sort of image, our molecule, we have a connection between these two nitrogens. Now, when we get the reflected mirror image, the nitrogen on the bottom is now connected really to this guy back here, which means it's going to create sort of a different angle. So every time you rotate it, this bond here is not going to match up with this bond, and there's always going to be something off, and they will not basically superimpose on each other. It kind of creates sort of a different sort of connection there. And that would be a chiral molecule because, again, the mirror image does not superimpose on it. Here again, we could take a look at our first one, which is our trans and isomer, and its mirror images are identical to each other. And our cis one is not going to be identical. So here, when we do the reflection, we really maintain our sort of same connections here between our nitrogens. So when we pull that out, we're not going to have any problem basically dropping that right on top of the original one because we have really the same connections. Again, here with our cis, we get that opposite sort of connection as we just talked about there with the nitrogens, and that sort of opposite way that is connected is going to create a different bond angle, and thus it's going to create something that's always going to be off. So in a lot of cases, your cis isomer will kind of create that. A lot of times you'll get that kind of bond that's going to be just off because of the mirror image. And a lot of times the trans isomer will be okay. It'll kind of superimpose on top of each other. Okay. So enantiomers are, again, two molecules that the mirror images of each other, and they're non-superimposable. And a lot of times these sort of non-superimposable mirror images, one works really well, say for something, and the other one has some different type of properties. So sometimes these enantiomers, although you have two guys that are related to each other, only one of them maybe has a certain property that's very helpful, say in drugs and stuff like that. All right. All right. So the next thing we're going to talk about is bonding in a electron model. And as you may know, formation of hybrid orbitals to share electron pairs, hybrid orbitals like sp, sp2, sp3, sp3d, sp3d2, right? So Vesper, which is our bonding model, does not work perfectly for complex ions. Again, we think of complex ions because we have these Lewis bases. It's more of a Lewis acid base sort of situation that's occurring where we have electrons being transferred and accepted. Hybrid orbitals are used by the metal, depend on really the number of ligands that are present. So here we have basically a coordination number of 6, 1, 2, 3, 4, 5, and 6 coming in. If you think about 6 electron pairs in like the Vesper model, that's your expanded octet, that's your octahedral arrangement, right? If you remember that there, and that has a hybridization of sp3d2, right? By the way, just count the letters, that's 6, right? 1, 4, and 6 there, if you count it all together. And it will do that. The hybrid orbitals require tetrahedral, square planar, and linear. So we have tetrahedral coordination number of 4, and that also is very similar to Vesper. We also have a coordination number of 4, which is square planar being the expanded octet, square planar right there with our octahedral, basically 6 electron pairs and 4 bonds. And linear is a coordination number of 2, right? So sp hybridization. And again, we have our sp3 here and our expanded hybridization happening over here. So common sort of geometry that goes with coordination numbers. Most of these are pretty straightforward. Coordination number 2 is linear. So again, kind of correlates to Vesper, right? 2 electron pairs, 2 bonds is linear. 4 coordination is tetrahedral. Again, 4 electron pairs, 4 bonds is tetrahedral geometry. But we can also get a square planar with the coordination number 4, which again would be more of expanded octet. And with a coordination number 6, as I mentioned before, that sort of correlates to the octahedral geometry. So most coordination compounds and even complex ions will go with one of these sort of orientations in terms of their geometry. And again, it is kind of related to coordination number. So coordination number 2, these guys usually will take a coordination number 4, and over here in our octahedral 6 in that case. Now, we're going to talk about what happens when transition metals have ligands present. And transition metals, obviously, as we talked about earlier, basically deal with d orbitals, and that's where they have a lot of their electrons that are involved in bonding. And as you know, there are 5 d orbitals there. Now, when we have really no ligand present and we're talking about the metal there, the transition metal, all of those 5d orbitals are basically all going to be the same energy. So they will all be basically equal to each other. The 5 individual d orbitals that make up that d subshell within the transition metal will be equal in energy. And that's important for how electrons go in or how our electrons are actually distributed. So obviously, if they're all equal in energy, we would put our electrons in like normal, right? One at a time. And then we would go back and start pairing up, right? Hund's rule, basically maximize parallel spin and then come back and pair everybody up there along the way. But now when these transition metals sort of come in contact with or near a ligand and start binding, there's actually a change in the energy of the individual d orbitals within that d subshell. And they actually split off differently in terms of energy. In this particular case, what we're looking at is actually coordination number of 6, and this is octahedral splitting here. And what you can see is we actually get 3 of the d orbitals, the xy, the yz, and the xz on the bottom. Get all of our squared guys up here, higher in energy. So there's actually an energy difference between the lower energy orbitals and d orbitals and the higher energy. That energy difference between them is what is referred to as crystal field splitting. Crystal field splitting is sometimes abbreviated with the delta symbol. It's also sometimes just abbreviated with the regular kind of change in energy sort of symbol. And that is the energy difference between 2d orbitals when a ligand is present. So why is this important? This is important because it's going to affect how the electrons in those d orbitals are basically distributed. So what happens is we always put electrons in lowest energy to highest, right, when they go into orbitals. So what's going to happen is we would start filling these guys first in this case because they are lowest in energy. And at this point, it has to make a decision of we normally would want to put an electron into each of the 5d orbitals before we start to pair them up. At this point, it would want to has to kind of look at the crystal field splitting and decide, is that a really big difference in energy? Is it like too high to go upwards to fill those guys first? And if they decide, nah, it's not that big of a difference between the high energy orbitals and the lower ones, they may continue to feel like normal and just kind of go through and just start, filling everybody like normal. But in certain situations, they will look at that energy split and go, no thanks, that's like way up there. I'm not going to go out that high. And they will decide actually to fill the lower ones first before they has to jump upwards in terms of the higher energy orbitals. So it can affect basically how the electrons are distributed in the transition metal when a ligand is present. And it will create different types of complex ions, as we'll talk about in just a second, in terms of how many unpaired electrons there are versus paired electrons. So we can calculate the crystal field splitting with an equation you should be familiar with from Chem 50. That's our energy equals H times our frequency. H is our Planck's constant, 6.63 times 10 to the minus 34 joule seconds. This is our frequency in hertz, our reciprocal seconds. That also is related to C is equal to the wavelength times the frequency. C is our speed of light, right? And 3 times 10 to the 8 meters per second. That is our wavelength in meters, and that is our frequency in reciprocal seconds. Gives us a speed of light of meters per second, right? And as you might remember as well, you could actually tie both of those equations together because if you solve for frequency, that is c divided by the wavelength, which means you can substitute that into here, and that gets you hc over the wavelength. So that allows you, if you know the wavelength associated with it or the frequency, you could calculate the energy change of those sort of d orbitals by just knowing those things. When we do some type of absorbance type of value here, right, and we're measuring, say, absorbance, we always want to pick the maximum wavelength, right? And the maximum wavelength means that we will get pretty much all of our samples on scale. If we pick a wavelength way over here, we're not going to get a lot of absorbance values. Here, we're going to get a lot of them underneath the thing. We also pick a wavelength that's usually the maximum absorbance to be the complementary color to what we see perhaps in the solution. So again, if our solution is red, we would not choose the red wavelength for our spectrophotometry because it's not absorbing red, because we're actually seeing red. It's actually absorbing, again, the complementary color to red. So if we wanted to calculate something like this, let's take a look at one. I think it's filled in, so we'll just talk about how we do this. The absorption maximum for a complex ion of this guy here was a coordination number of 6, occurs at 470 nanometers. What color of the complex, or what is the color of the complex, and what is the crystal field splitting? So as we just talked about a second ago, the absorbance occurs at 470, which is here in the blue, which means really the solution will appear to us complementary to blue, again, which is in the orange. So our solution should look orange in this case. And obviously, I think we had our iron experiment, and you chose a wavelength in this area, more of the greenish bluish type color. Again, that is the complementary color to that. To calculate the crystal field splitting, it's really the same equation. So we could use HC divided by the wavelength. Since we have the wavelengths given to us, we do have to convert our nanometers into meters. And in 1 nanometer, there's 10 to the minus 9 meters, basically. And we can do our conversion there. So that is where that comes from. And that is our H, that's our C, and that obviously is our wavelength in meters. That will give us the energy associated with that wave. And we want to know what is it per mole. So this is basically joules per atom. And that is why we then use our friend Avogadro's number to convert it into basically joules per mole or kilojoules per mole. So here we would multiply by Avogadro's number up on top per mole, basically. So the atoms would cancel, and that gives us basically joules per mole, and we can convert it to kilojoules per mole. So the energy split here is 255 kilojoules per mole. Any questions on that calculation there? So how do we know if we are going to get kind of a big split between the lower d orbitals and the higher d orbitals? It does has to do with what ligands are present. And there's a spectrochemical series here. And on the left-hand side, we have what are referred to as weak field ligands. And on the right-hand side, we have ones that are referred to as strong field. So if you have a weak field ligand, what that means is when this thing sort of splits off into its orbitals, and again, we're still looking at the sort of octahedral arrangement there. What's going to happen is this difference here is going to be small. So when the electrons get distributed here, they will go 1, 2, 3, and this side, and that's not too bad, and we'll just kind of feel like normal. Basically, they will populate like normal. Now, again, if you got this splitting here, and we have one of those strong field ligands, so this is a weak field, you would have this difference here that's large with our strong field. And when they would go to fill in, they would go 1, 2, 3, and decide not too much energy. They're going to go this way first. And then only when the bottom is completely filled, then they will start populating the top if necessary. So The result of this is, as you can see in just sort of this example here, you will end up with either more unpaired electrons or more paired electrons, right? So paired electrons are electrons in the same orbital with opposing spin, right? MS is a +1/2, -1/2. So this is what is sometimes referred to as a high spin complex. And a high spin complex has a lot of unpaired electrons. And this is what was to be considered a low spin complex. And a low spin complex has a lot of paired electrons, not so many unpaired electrons. So very common questions on these type of problems is like how many unpaired electrons are there in this sort of complex? And is it high spin or low spin type of complex? Now, what do you do if you're kind of in the middle? Kind of in the middle, a lot of times they will perhaps tell you which way to kind of do it. They'll tell you maybe, do it for the high spin complex or the low spin complex. And in some cases, it may not make a difference. So if they don't tell you it's high spin or low spin, and you're not sure what type of ligand it is, it may not make a difference because there's just not enough electrons regardless to go up or down. There's only a couple, so it really won't matter if it's high spin or low spin. Those are always going to end up on the bottom in a coordination number here of 6. So if you have if you have 3 or less electrons, it really won't make a difference because you will just always populate the bottom here no matter what. So sometimes it doesn't make a difference in terms of that. All right, so if we look at one here, for example, if we look at our nickel Br6 with a -2, so if we take a look at this guy here, the first thing we want to think about is what we got going on in terms of the oxidation state of our metal. So we know that Br here is -1, and there's 6 of them, so it's -6. Overall, we have a -2. Which means the nickel here is a +4. And if we look at nickel there on the periodic table, nickel with no charge there, there's nickel, there it is, 28. So nickel is argon, 4s2, and 3d8, I believe. And when nickel loses its 4 electrons, when it becomes nickel with a +4 charge, it's got 24 electrons. So as we talked about earlier on, when transition metals lose electrons, they are going to lose the S's first. So we're going to take 2 out of there. We will also then have to then take 2 out of there as well. And that's going to leave us an argon 3s 3d6. So what we're talking about here is basically there are 6 electrons in the d orbitals for nickel in this situation. We need to think about how it's going to be distributed. Here again, the coordination number is 6, which means this is going to be our octahedral splitting that we were just looking at here on the previous page. We also want to think about Br, which is the ligand, and the Br over here is a weak field ligand. And that means when it does its splitting, we're going to get our 3 d orbitals on the bottom and our 2 up on top. And this crystal field splitting is going to be small because Br is weak. And what that means is when it goes to distribute its electrons, and we're talking about these 6 electrons that it has to distribute, it is going to go 1, 2, 3, and this is going to be a weak field, which means it will continue to distribute them like normal and then roll back down. And what we would end up with in this case is 4 unpaired electrons. And this would be considered a high spin complex, because obviously we have a lot of unpaired electrons happening. Questions on that there? All right, so why don't you try the other ones here and see what you come up with. So why don't you draw the crystal field splitting for these guys and figure out how many unpaired electrons does each have? Iron is 26. No charge. Start with this one here. So here we have NiEN3, 4 plus. Coordination number here is going to be 6. Remember, En is bidentate, and there's 3 of them, which means we do have a coordination number of 6. This also will be our octahedral splitting. En is 0. Which means that the nickel here also still has the +4 as it did above. So we will end up with the same number of electrons that needed to be distributed. Difference here, though, is we have En, which is more of a strong field ligand. So what that means is when we get our splitting here that's occurring, this is going to be large, and that's again because it's a strong field. So when we go to distribute our 6 electrons that we had there, we're going to go 1, 2, 3, and it's going to decide that is too big. So we're just going to fill down here first, 4, 5, and 6. In this case, we'll actually have no unpaired electrons, right? And this definitely would be what's considered a low spin complex, as it has pretty much no unpaired electrons in that case. Any questions on that one there? All right, so let's take a look at the next one, which is we'll do this guy up here. So we have iron and there it is. We have iron and fluorine, I think. Iron and fluorine. Also at 3 minus. Once again, here, coordination number going to be 6 because of the fluoride, which is monodentate, and there's 6 of them. And again, this is going to give us our octahedral splitting. So on this one, I said we'll do it as weak filled. So that means when we do our splitting here, we're going to have a small sort of difference. And here we do want to figure out what's going on in terms of charge. That's -1, -6. That means that our iron here will be carrying a +3 charge. When we look at iron with no charge is 26, that gives us a argon 4s2 3d6 with a +3 charge. Going to lose 3 electrons. It's got 23 electrons. So again, we're going to get rid of those 2 there. We'll take out one of those guys. That's going to leave us an argon 3d5. And it's those 5 electrons that need to be distributed here into our orbitals. And in this case, we will go 1, 2, 3. This being small means no big deal. We'll just go up. And in this case, we actually have 5 unpaired electrons. And that would definitely be a high spin situation. Now, again, if we did it for a strong field, and you were told to do the same guy for a strong field, so because it's kind of in the middle, that would give us large here for strong field. And when we go to distribute this 1, 2, 3, and they will actually come back this way, which would give us more of a low spin complex with 1 unpaired electron. Any questions on that one there? The last one is that guy right there. So that's the iron with the CN6. And we look at CN, it's over here at strong field. So what we're going to end up with here is iron is -1 here for the Cn. That's -6, -3, +3. So in this case, we will still have our 5 electrons. And because Cn is strong filled, it's basically going to end up like this guy right here. So I'll just steal this one I just did there. It will basically be this one. Again, with that strong field ligand, give us a large separation. We're going to get more paired up, and again, a low spin situation in this case. Any questions on how to do those there? Did you need to be able to draw the diagram there, figure out how many unpaired electrons? Again, low spin, high spin, very common sort of questions on these type of things. What we've been looking at specifically here with kind of our 3 and 2 splitting is for coordination number of 6 and octahedral arrangement in terms of geometry. Now, it is a little bit different when we have different coordination numbers, but here's an example. What we were just looking at, we have our high spin here, a lot of unpaired electrons, and again, our lower spin complex there with a lot more paired electrons happening. Here's just an arrangement of a lot of high spin complexes. We're just going to get a lot more unpaired electrons. Low spin, where we have a stronger field, bigger separation, we're going to get a lot more paired up electrons. Now, when we talk about the crystal field splitting that occurs in a tetrahedral complex would be a coordination number of 4. And remember, with a coordination number of 4, you can either get tetrahedral or square planar in terms of its geometry. And if we do have tetrahedral, you can kind of think of it as almost the exact reverse of the one we just did. In this case, those 3 that were on the bottom end up on top, higher in energy, and those kind of squared orbitals actually end up lower in energy. It works the same way. You would figure out, obviously, in this case, how many d electrons you have available to you in the transition metal. And if you had a weak field, it would feel like normal. It would just go through and fill up like normal. If you had a strong field where it's too big of a difference, they don't really want to hop up there, it would also feel kind of like normal. It would just come down before it obviously will go up as well. So it works the same way. It's basically the opposite of octahedral splitting. Now, it gets a little bit crazier when you get into square planar, which is also a coordination number of 4. And you can see you got a lot more differences in terms of where all those orbitals end up. And again, this is because we have some expanded octet happening, some extra electrons in there as well that sort of make these orbitals kind of split out at different distances. Works the same way. Again, always they fill lowest to highest, so you kind of work your way up as well. So for us, you're going to be responsible for our octahedral splitting, which is what we did here with those examples, and also tetrahedral. So we'll go with those 2, which are basically opposites of each other. You will not have to worry about square planar sort of splitting or anything like that. Any questions on that there? All right, that wraps up this chapter here. And we're then going to go to, I think, probably the last one of the year here. We'll go with that one. All right, so the last chapter we're going to talk about here is, last chapter is going to be nuclear chemistry. And in nuclear chemistry, it has to do obviously with radioactivity. So let's talk a little bit about radioactivity here. Radioactivity are radioactive nuclei that will basically decompose into smaller nuclei in sort of a spontaneous process. That is what is referred to as radioactive decay. We say that if something goes through that, it is unstable. It typically will continue to sort of decay until it hits something that is sort of considered stable. And at that point, it hopefully should be done. When we have sort of a decay process that occurs, what we start with is sometimes referred to as the parent nuclide. And that's sort of referring to the nucleus, because nuclear chemistry is basically all about what happens in the nucleus with our protons and our neutrons. And what is sort of made as a result of that is what is known as the daughter nuclei. If you look on the periodic table, pretty much 84 and above, things with 84 and above protons are usually radioactive, especially on those bottom row there. You got a lot of those guys that are those man-made sort of elements and stuff like that. When we talk about radioactivity, there's several types that we come across definitely in this chapter. And our friend Rutherford, if you remember right, he did that gold foil experiment. He shot things like alpha particles at pieces of gold foil to sort of investigate the atom. Alpha particles or alpha rays have the symbol of the alpha symbol. They also are essentially a helium nucleus. So in nuclear chemistry, you will see alpha particles abbreviated with the alpha symbol. Our people will also just use helium as well to represent it. So both of those are very commonly used. By the way, the top number is which number? That is the mass number, yeah. And bottom number is the atomic number, right? The atomic number is the number of protons, right, there are in an atom. You can find that on the periodic table. That is the number above the symbol. The mass number is the number of protons and neutrons there are, right? So that is protons and neutrons. And this are protons. Can you find the mass number on the periodic table? The answer is no, you cannot find the mass number on the periodic table. The number on the bottom is not the mass number. That is the atomic mass, which is different. The mass number, atomic number, number of protons, electrons, and neutrons, they all should be positive whole numbers. So a good way to remember that is the number on the bottom there is usually not a whole number. Beta particles or beta rays, they're basically electrons. They have kind of like a negative charge. So this is kind of like a positive radioactive guy. And it's kind of like a negative guy. And beta particles also are used as the symbol, or electron is also used as the symbol for it as well. We also have gamma rays. Gamma rays are really just pure energy. If you remember the electromagnetic spectrum, that's usually at the end of the electromagnetic spectrum, very short wavelength, very high in energy. And usually that's kind of the symbol used for gamma. In addition, there's some other symbols that we'll see in nuclear chemistry. We have positrons, which is an electron with a better attitude, it's positive. And it also uses the same symbols, except that it is positive one instead of negative one. And sometimes, as we will see, they will undergo a process known as electron capture, which is really just an electron, basically. As I mentioned a second ago, we have our symbols, which are very commonly written. Again, on the top left is our mass number. On the bottom left is our atomic number. And again, if you want to know the number of neutrons, you could find it by taking our mass number minus the atomic number. We'll give you a number of neutrons. Here are some other sort of symbols that are very commonly used. A proton is sometimes abbreviated with a P, a 1, and a 1. Also, hydrogen is used as a symbol for a proton. And a neutron, very commonly used a lot, 1 over 0 there, and an N is used. As I mentioned before, electrons and beta particles and positrons, they really do have the same symbol. I would say if you come across a problem where it just gives you the beta symbol, it most likely is going to be a beta particle. They usually will, if it's a positron, do something to indicate that it is the positron. So sometimes they'll even put a plus on top of it to indicate that it is a positron, or they definitely will put the sort of numbers in there as well. So I would say if you just see a blank old beta sort of symbol in a problem, probably a safe bet to assume that it is a beta particle and it's not a positron. So they usually will sort of try to distinguish that positron from the beta particle. Now, when we talk about radioactivity, depending on the type of radioactivity that is being used, it can penetrate farther into your skin, and also lead. As you can see, their alpha particles do not penetrate as far as, say, beta particles, and gamma particles penetrate pretty far. That's why if you're doing anything that involves radioactivity, you should really know what type of emitter it is, because that's really important in terms of the safety that you should use. If you're using a gamma emitter, you definitely want to use some good protection for that, so you're not just getting absorbed by gamma rays and stuff like that. Um, and if you're using something as an alpha emitter, you might not need as much sort of protection if you're working with something. So it's really important if you ever work with anything that you figure out what type of emitter it is so that you have the proper equipment. So let's talk a little bit about balancing nuclear equations, which is like super hard and very complicated. It's really not. You just need to know how to add, I suppose. So that's all you need to know. So when we balance nuclear equations, it is different than when we balance regular equations. And the reason for that is in a regular chemical reaction, we have conservation of the elements. So if I started with 4 carbons, I end with 4 carbons, because in a chemical reaction, the only thing that you're doing is breaking bonds, which are electrons. In a nuclear reaction, you're doing pretty much always everything in the nucleus, and you're playing with protons and neutrons, which means we do not have conservation of elements in here because protons are changing and we make new elements. Out of protons, electrons, and neutrons, as you hopefully know, it is the protons, right, that determine what element you're dealing with. So because nuclear reactions happen in the nucleus, protons are sometimes converted to neutrons. Neutrons are like converted to protons. So we actually don't have that conservation of those elements. So the way that we balance nuclear equations is we just want to make sure that when we add up all the mass numbers on the left-hand side, they equal the mass number on the right-hand side. So if we look here, that's 235, and 1 is 236. Over here, we got 138, 96, and 2, by multiplying that out, gives us 236. So we're balanced. And then what you have to make sure of is on the left-hand side and right-hand side on the bottom, all the atomic numbers equal each other. So that's 92. That's 55, 37, and 0 is 92 as well. So this would be considered a balanced nuclear equation. So very commonly, a couple of the ways that we come across these type of things is perhaps, maybe something is missing. So really, if something's missing, you want to figure out what is missing. It really is the atomic number that will tell you that. So here we would have 92. On this side here, we have 37, basically. So we know that the missing guy to get to 92, basically just subtract the 2, would be 55. Then that's where the periodic table comes into play. You just go to the periodic table and you find number 55 there. And obviously 55 is what we have here, which should be our cesium. And then for the mass number, what we would do again is we would add this up and go 236. We got 96, and we do need to multiply here, and gives us 2. So we basically got 236 minus 98, and that will give us our missing mass number in this case of 138. So that is very commonly how you would sort of solve these type of things. In addition, you may be given a problem, as we'll do some examples further in this chapter, where it tells, hey, this thing goes through a alpha emission, or this is a beta decay, or something like that. You kind of have to predict the equation. When you're told those things like, hey, this thing decays through alpha emission or beta decay, anything that goes through those type of things, those particles end up on the right-hand side of the arrow. If you have anything that says you bombarded something with like a neutron, or you have an electron capture. So bombarding or electron captured, those particles go on the left-hand side of the arrow as like reactants. So that's sort of words that sometimes you see as you go through it. All right, I think that's a good place to stop, actually.